Hello. Our project is about human body part segmentation and matching between poses. Shimon was responsible for the architecture of the network, and I was responsible for the feature extraction and body part matching.
The segmentation architecture we implemented is made up of the 16-layer variation of the VGG network and then 2 convolutional layers over here, followed by 5 up-convolutional layers that upsample in the spatial dimensions. Additionally, there are skip connections from the contracted part of the network. The skip connections apply a convolution followed by dropout. The features are then cropped to the correct sizes and summed together. Okay. The paper uses a layer-wise training approach where they train the network with a single up-convolutional layer and then fix the weights and add the next. The network takes a while to reach good results, so experimenting with layer-wise training was not feasible for us. Here are some of our results. We achieved a 6.94% IOU averaged over all of our 6 body parts. The paper doesn't present results for 6 body parts, but on 4, they achieved 78.23 and 71.7 on 14 body parts. Here's the IOU for all of our 6 body parts. Their results are clearly significantly better, which is a result of much longer training. Here is an example from the test set, and we can see our prediction versus the true mask. And here's an example that is not from the test set, that was just pulled from online, and we can see quite a good prediction in this case.
And the second part of this project is to match between body parts. Well, traditional feature descriptors like SIFT can very much fit our needs here, but we wanted to take a deep learning oriented approach by using a learned descriptor. VGG16 naturally came to our mind since it was the feature descriptor used by Olivier in the previous network. As shown in the diagram, we decided to use the first 2 convolutional layers as feature extractors since they provide pixel-wise information over the whole image, while layers after the first max pooling operation will not provide us information on the entire image. The idea of the body part matching is to use the segmentation of body parts from part 1 to limit the matching to be between the same classes only. That is, a left arm can only be matched against other left arms. This can greatly improve the performance and accuracy of our matching. However, the VGG16 features are available for every single pixel as opposed to just the key points. Hence, we have to be selective in terms of the points to use. This algorithm that we came up with selects the key points to be relative center of its classes. Basically, a point xy is a feature point if and only if all points in a k by k window centered at the point all have the same class as xy, where k is a tunable parameter. For example, if xy belongs to the class torso and we have k equals phi, then all points in the 5 by 5 matrix centered at xy should all be torso in order for xy to be considered a key point. Here's one of the results we get. We can see that clearly one of the left hand is being matched against the left hand even though it has moved between the frames. For future work, we would like to train the network for much longer and experiment with layer-wise training mentioned in the paper. And for the matching, we would like to experiment with features more related to human bodies as opposed to using a generic feature descriptor like VGG. Some of the challenges we encountered during this project was due to limited time and computational resources. The original Olivier paper trained the network for much longer than we did, while having better GPU and hardware resources than we do.